morning. While addressing the quantification of damages in the last lecture, we introduced the term dose. We said dose consists of maybe one or two parameters which describe the consequence of an explosion, namely, like for instance, from an explosion you have an overpressure, maybe you have the impulse. Well, you could have something like heat radiation from a huge fireball in the aftermath of an explosion, or else you could also have effective time over which the fireball lasts, and maybe either singly or collectively, like in some cases where overpressure and impulse could result in toppling a person or in damaging a building, or overpressure alone could result in maybe leading to the loss of hearing, like rupturing the eardrum. Therefore, you could have different types of consequences of the explosion. These are the parameters, and one or two of them or more combined together is what we called as a dose. For example, let us repeat this again. Supposing we say, well, the hearing, that is, let us say rupture of the eardrum. Eardrum is something which responds to very high frequencies, and therefore overpressure delta P from the explosion is sufficient to burst it or rupture it. Then in that case we say, well, the dose can be represented by overpressure in Newton per meter square. We also said maybe when we look at different dosages or different overpressures, and what did we tell? Well, I could plot, let us say, the dosage in terms of the overpressure delta P in this particular case, and I say, well, if you have an overpressure of the order of, let us say, 34 kPa, then maybe many people lose their hearing. But we also said some are more vulnerable than others. For in some cases, maybe a lower level itself causes the ear to get, or the eardrum to get ruptured. In some cases, maybe people are so resistant that even a larger value of overpressure they can withstand. Therefore, we say, well, this is the fraction, or we said that the fraction of people who are getting affected, and this is something like a Gaussian distribution, and we said, well, I could represent it by, if I denote this scale as x and this fraction as a probability fraction, I could write it as Gaussian distribution as equal to 1 over root 2 pi into sigma into, well, this is the mean value who get affected at this value, which is a mean, we get e to the power minus x by mu, x minus mu whole square divided by 2 sigma square into dx. Well, I am talking in terms of a probability fraction, therefore, there is no integral, it is just into exponential of this, there is no dx either, therefore, the probability is this, and this gives the probability fraction. Now, what is it we are saying? Well, some people get their eardrum affected at a lower value of overpressure, some are resistant even at a higher pressure. And if we were to take a look at this in terms of dosages, well, an average dose is 34 kPa overpressure, some have it at lower value, some have their hearing impaired at the higher value. And what does this give us? Let's take a look at it. If I am going to take a look at the total response or the total number of people who are affected, then I say, well, I again replot this figure over here. I say, well, I am now talking of the response, or rather the total number of people who are getting affected. Well, for this low level of overpressure, a small number of people get affected. At this value, well, some more get affected, this plus this much gets affected. For the mean, well, some more people get affected. And now we are going, well, the increment is little smaller, the increment gets smaller, and therefore, the total response or the total number of people who are getting affected goes as maybe something like this. You know, this curve is something like a sigma, that is the letter sigma, and we call it as sigmoid. And this gives the total response as a function of the dosage d, and it has a sigmoid shape. Now, the total response for a given dosage, well, this is for this dosage, well, this is the number of people who are affected. Well, when the dosage is extremely large, well, all the people are affected. This is 100% over here, and this is something like a cumulative distribution, rather the total number which we called as cumulative distribution. And what is this cumulative distribution function? Compared to Px, which is the probability distribution function or a Gaussian distribution function over here, you say Px going from minus infinity to x dx is what we call as the cumulative distribution function, or rather here the total response is nothing but maybe up to this level, let us say d1 over here, this is the cumulative number, up to here it is the cumulative number, and therefore this cumulative distribution is minus infinity to x, because on the left hand side I start from minus infinity to the right side of plus infinity, because the total value of in this particular Gaussian distribution is minus infinity to infinity of the standard distribution function, the area under this curve is 1. Therefore, you have the cumulative distribution given by phi x is equal to minus infinity to x of Px dx, and well, the cumulative distribution function is the total response. Therefore, for any dose like we have, in this case we are talking of overpressure, maybe I could have a dosage, and the dosage for maybe radiation could be something like intensity of radiation to the power 4/3 into the effective time over which radiation is there. I have a similar figure. In other words, I call this as a dose, and then I plot, well, the cumulative distribution function tells me response or the cumulative value as a function of dosage. Well, it looks like this. We have a series of such curves, and these are known as dose response curves. The thing to note is all the dose response curves are something having a sigmoid shape and therefore are somewhat non-linear. We would like to make use of the dose response curves and still define the or quantify the destruction due to an explosion, and that is what we are saying. Is it possible to have another parameter which does not have this non-linear shape, and somewhat can I have something like a shape wherein r versus sigma is little more uniform or little more linear, such that I can always use such type of response over the dose curves. You know, since the dose response curves tends to be important not only to get the hazard of the explosion, but also find out the acceptable doses at which the response is small, or you do not have many people dying or many people getting affected or many buildings being shattered. You know, since these dose response curves are important, we also looked in the last lecture at the value of response versus dose. We talked of a very heavy dosage wherein things were fatal, this is let us say 100% line, and when we had a lethal dose, that means people dying, well, the curve was like this. That means you had, this is the starting point at which maybe people started dying, this point at which all the 10% everybody who got finished. You have in between a 50% line, admit we called it as lethal dose 50, well, this was the lethal line for the dosage. We also had another curve which we called as the ED line, sort of the effective dosage, and the effective dosage, the shape was little different. That shape was something like this, little more, this was almost vertical, this went more like started gradually, had a longer range of dosage, and this was something like effective dosage 50. That means 50% of the people got affected at this level of dosage, that is T50. The D0 for effective dosage is here. This is the value corresponding to 100. When we say effective dosage, it means that yes, people are affected, but the influence on people could be reversed by treatment and all that, and therefore we called it as effective dosage. In between the ED, effective dosage, and lethal dosage, we could have something like a toxic dosage. This is mainly from spills, wherein maybe some permanent harm is done. Here also you have TD, toxic dosage 50. This is the toxic dosage line. You have a lethal line, you have a toxic dosage line, you have the effective dosage line over here. Now, if you see these three curves, the level of dosage in the case of toxic or in the case of the lethal dosage is very high, because apparently you are finishing. It is also steep. Therefore, if I were to plot the probability distribution, let us say Px as a function of x, x denoting the dosage d, what is it we will get in this case? In the case of the toxic dosage, well, the curves would be somewhere over here. This is the shape of the Gaussian distribution. Whereas, when I talk of effective dosage, well, the curve will be a little more smooth, little more uniform, something like this. Well, in this case, maybe the standard deviation or deviation is larger, standard deviation is larger. In this case, the standard deviation is smaller. Therefore, whenever we talk of high values and a small range over which the entire dosage affects the response, and we are interested in in terms of the response versus the dose response curves. In this case also the area under both the curves is unity, but in this case it is much more peaked over here. That means a small range of high dosage causes the lethal effect, a large range of dosage in this case causes the effect over here. Of course, whenever we are talking of dosage, the dosage here is different from the dosage over here. The two curves should not be drawn on the same axis, but this is what I have drawn over here. Therefore, what I find is, well, this is for the lethal dose, this is the distribution over here, this is for the effective dose over here. Well, mind you, as I say, the x axis in the two cases are not the same. It becomes necessary for us, before we go further, to be able to look at the standard deviation in some detail, because as I said, the range here is smaller, whereas the range here is larger. Therefore, let us take a look at standard deviation in the context of, let us say, the Gaussian distribution. What does the standard distribution really represent? You will recall we had talked about it when we discussed atmospheric dispersion. And now if we take a mean value, mean is 0, let us say, and we say, well, I have a Gaussian distribution Px over here. This is equal to Px, which we said could be written as 1 over under root 2 pi sigma into exponential of minus x minus mu squared divided by 2 sigma square. Now, what does the standard deviation represent? Well, here I have a standard deviation, here I have a standard deviation. I say this value is minus sigma, this value is plus sigma over here. I take twice the value, that means I take another value here which is equal to this distance. This I say is equal to minus 2 sigma, and similarly I take a value, another sigma over here. Well, this becomes 2 sigma. I still do one more exercise. I take 3 sigma, sigma plus sigma plus sigma. This becomes 3 sigma over here, minus 3 sigma, to something like plus 3 sigma over here. What does this sigma represent? If I take the area of the curve, and I take the area of the curve between minus sigma to plus sigma in the standard distribution, that's the Gaussian distribution, then that is the standard distribution. The area of this curve comes out to be equal to area between minus sigma to plus sigma is equal to something like 68.3% of the total area. Mind you that the total area from minus infinity to plus infinity is 1. This is 68.3% of that. If I take from minus 2 sigma to plus 2 sigma, which means I take the area of the curve between this minus 2 sigma, that is from here to here, the area of the curve is something like 95.4%. Between minus 3 sigma to plus 3 sigma, the value is something like 99.7%. Well, I can keep on doing this. Maybe I go to 4 sigma, let us say. I go to something like 4 sigma over here, minus 4 sigma to the mean 2 plus 4 sigma over here. I take another sigma over here, 4 sigma. The area of the curve minus 4 sigma 2 plus 4 sigma is something like 99.994%. That means I am covering almost the entire distribution. What is the physical significance of the standard deviation? Well, the standard deviation is something which tells, now if I were to do an experiment, let us say an experiment in a lab, and I say, well, my certainty, my confidence in the experiment is between, let us say, minus sigma to sigma level, which means that is my confidence is up to the sigma level, then I mean I am sure that my experiments are certain within 68.3. That means the chances of, if I do any other experiment, most likely 68.3% of the times the point will lie within the range what I have done or within my particular experimental trends. That means it tells us something like the confidence. But we must also remember that when we are talking of sigma, we are going along the dose axis or along the x axis. Therefore, to a large extent, when I come back and look at this cumulative distribution, that means the response over here, if my value of this value, we are talking of sigma values which are somewhat smaller. That means maybe my minus 3 sigma to plus 3 sigma is within this. That means it is a very marked sort of a distribution is like this compared to a distribution like this. But since we are talking in terms of cumulative distribution and our importance is not on sigma alone, but on the Rho's response, upon the dose versus the response curves, I would like to still try to see whether it is possible for me to have something like a linear relation between the dose and the response. For this, I again revisit the cumulative distribution. What I do is, I say, well, phi x is equal to 1 over root 2 pi of the standard deviation. Mind you, we again come back, we will come back to the standard deviation into minus infinity to the value of x over here into e to the power minus x minus mu whole square divided by 2 sigma square. This is the value of the cumulative distribution. Now, if I can have a transform, something like I transform my cumulative distribution by taking inverse of it itself. Rather, I say, if I can take inverse, I can take inverse of the cumulative distribution itself, phi of phi x. What is it I am meaning? If I say phi inverse phi x, I know the answer is x. Like we take Laplacian transformation and I take inverse of the Laplacian transformation of, let us say, y. Well, I take the Laplace transform and I take inverse of the Laplace transform. So, also I take the cumulative, that is inverse of the cumulative distribution, and I take inverse of the cumulative value. That means I take inverse of the cumulative distribution of the cumulative distribution itself. I get back my x axis, and along the x axis is what we have is the something like the standard deviation along the x axis. Therefore, let us try to understand what I mean by this. And if I take the value of the inverse of the cumulative distribution, I get along the x axis. Therefore, let us see some values so that I can make some sense of it. And if this definition is what is known as a probability unit, which is known as PROBIT is known as probit. But we must understand this before I start doing anything on probit. Therefore, let us take a look at this particular distribution over here. I said that the area between minus sigma to sigma is 0.683. Now, the area under this curve gives me the cumulative distribution, that is the total value, and therefore, I can say phi of minus sigma to sigma, or let us say phi of minus sigma is equal to what? Can I get the cumulative distribution up to sigma? Let us see if that is possible. Let me do it over here. Let us say I am interested in phi x. Phi x is up to any x. Now, I am interested in phi of, let us say, minus sigma. If I say I am interested in phi of minus sigma, I am interested up to this particular point. That means I am interested in the cumulative or in the area up to this particular place, and the area up to this place is equal to, let us see what is the area of the cumulative distribution. The total area is 1. The area up to the center line up to here is 0.5 because it is symmetrical. I considered the value of mu corresponding to the value of x is equal to 0. Therefore, I have is equal to 0.5 minus the total area between minus sigma to plus sigma we said is 0.683. Therefore, it is going to be this, I subtract this portion, that is half of it, minus 0.683 divided by 2, which is equal to 0.5 minus 0.34, let us say 341, which is equal to, or let us say just say 0.34, which is equal to 0.16. This is the value of the cumulative distribution up to minus sigma. If I am interested in, let us say, up to minus 3 sigma, phi of minus 3 sigma, what is the value I get? Well, I get up to this I want. I know from here to here it is symmetrical and the total area is 0.997. Therefore, I get it is equal to half minus 0.997 divided by 2, which is equal to 0.003 divided by 2, which is equal to 0.0015. Similarly, let us write one more value. If I were to say I am interested in the cumulative distribution up to plus sigma, I am interested in a value somewhere over here. This is the value, and what is the value I get? I have 0.5 plus I have this value, that means 0.5, 0.5 plus 0.683, which is up to sigma divided by 2, which is equal to 0.84. Now, I have maybe the value of phi up to minus sigma, the value of response or the cumulative distribution up to minus 3 sigma up to plus sigma, and so on. Now, if I were to take the inverse, if I take phi inverse of phi of minus sigma, well, it gives me minus sigma, because phi inverse of phi, that is, I take inverse of the operating the inverse function again on the function is the value over here, but minus phi sigma is equal to, we just now said phi of minus sigma is equal to 0.16. Therefore, I can say inverse of 0.16 is equal to minus sigma. So, also I can say, well, minus 3 sigma phi inverse of phi of minus 3 sigma is equal to 0.0015, or rather phi inverse of 0.0015 is equal to minus 3 sigma. And similarly, I said phi inverse of 0.84, let us write it down, phi inverse of 0.84 is equal to plus sigma. Therefore, we see that the inverse of the cumulative distribution gives you something like the standard deviation or along the x axis, the distance along the x axis, because we are talking in terms of minus 3 sigma to plus 2 minus 2 sigma minus sigma 0 plus sigma 2 plus 2 sigma plus 3 sigma plus 4 sigma and so on. And this value of when I say phi inverse, that means you take the inverse of the cumulative distribution is what we call as a probit. That means we are converting the cumulative distribution into the length scale along the dosage line, and this is what we call as a probit. But when we say the probit, we do not want to end up in numbers along the x axis in terms of, let us say, a negative number and positive number. Therefore, we refer to the probit for a base or for a reference of 5 sigma. 5 sigma is what is normally adopted, and therefore, we say, well, phi, I refer to the thing as y minus 5, or rather my cumulative distribution now becomes equal to 1 over under root 2 pi sigma into, I have minus infinity into probit minus the value of 5 sigma into e to the power minus x minus mu whole squared by 2 sigma square. I think I should again sort of repeat to some extent what we mean by probit. By probit we mean the inverse of the cumulative distribution of the cumulative distribution. That means the inverse cumulative distribution of the cumulative distribution, which gives back the x axis, and normally this is the value of y, and therefore, you find that yes, this is what I am looking at, maybe the value along the x axis which we said is probit, and now instead of choosing y, I choose a value with respect to minus 5 sigma, such that I am way back over here. I refer to this such that even if I get a number here, it is going to be positive. Even a very small number, we said 4 sigma corresponds to 99.994 of the area. If I take 5 sigma, it is going to correspond to 99.9999 something. Therefore, it is always going to be positive, and to make sure that you get a positive value of y, we choose the base as 5 sigma. Therefore, this is how a probit is, and why we use a probit is maybe we are interested in having the response curves, namely the dose response curves, and what we are really looking at is response is nothing but the cumulative function phi x, which is the response. We are having the dose curves. In practice, we get a curve like this. We would like the dose response curves, the response which is cumulative, instead of d, if I were to plot it with respect to y over here, maybe I plot response versus y, well, the curve will be a little more linear, so that I can use my linear approximation and I will be able to do these things without really looking at these statistical relations. Nowadays we have computer, we always use formulae and do it, but if somebody wants to do it on the field, it is much easier to use a linear relation, and this is what I show in a slide. I will be showing it shortly, but what I show is I will show the values of the cumulative response as a function of y, and how is y defined? Y is defined as y minus 5 sigma, which is the probit, and this is given by the inverse cumulative distribution function of the cumulative distribution function, which gives me back the value of this. Actually, here it should have been x over here, and this is what I denote by probit and call it as y. Actually, it is getting back on the x axis, where actually I should have got x, but I call it as y to term the value probability unit probit. Therefore, let us take a look at this particular figure over here. This is the cumulative distribution R, which is the response, which is cumulative function, that is phi, and this is the value of the probit. When the probit value is 3, the response is 2.3. That means we are plotting the cumulative value over here. That means for 3, that means instead of plotting the dosage, I am plotting now y over here, or instead of plotting x, I am plotting it as capital Y. When the area of the curve is 6.3%, the value of y is 3.5. For 15.9, the value is 4, and so on. This is the value. And what I get is, I get a curve something like this, which is little more linear. It is linear in the range between, let us say, 4 to something like 6.5 values of y, for which the response varies between something like, normally we are looking at responses between 25 to 90%, for which it is fairly reasonably linear. And such a linear relation is what I show in the next slide. People use the linear relation of the response as a function, that means the cumulative distribution as a function of the probit y as 38.2 y. This is just a curve fit of the previous figure which I have over here in this particular range. For values between, let us say, 5% response to something like almost 90% response, I get a curve over here, and this curve is fitted by a cubic equation for probit as R is equal to 3.25 y cube plus 48.76 y square minus a coefficient 206.6 y plus 270.35. Therefore, what the problem really reduces is if I can calculate the value of the probit y, I can directly get the value of R, and that has been the endeavor while talking in terms of quantification of damages, to be able to express the damages in terms of probit y. Let me again go to the board and clarify this particular point. What is it I mean? We said that the response is a cumulative distribution function, wherein you say phi of the dosage as a function of the dosage, and you have the cumulative distribution which starts at a value, let us say d0, and this is where here all the people or the total response is available, and this is what we say dose response curves. Instead of having dosage here which gives a sharp sigmoid type of a shape, all what we do is you take the inverse cumulative distribution of this cumulative distribution, and you have phi inverse of phi, which for any dosage d we could write it as maybe any dosage d could be written as the dosage d itself, and this is what we call as y, when the value of capital Y is based on a standard deviation of minus phi sigma. That means I call this y as y minus phi sigma, or since along the x axis I have sigma, therefore this becomes y minus 5. This is maybe I start with minus 5 sigma, and therefore this becomes my value of the x axis, and this becomes the probit as it were. Therefore, instead of plotting the response curves like this, I show the response curves as a function of y, in which case it is more linear and it is something like this. If I were to consider this shape itself, well, I could also fit in a value of r as a function of maybe y cubed, y square, y. If I am only interested, normally we are interested only in this range, in which case I can say r is equal to ay plus b, which is a linear curve. That is y is equal to mx plus c over here. Therefore, we need to now get back to what is this probit parameter. We say y is a probit, and therefore, let us take a look at what this probit parameter could be expressed as. Instead of writing the cumulative distribution as phi of x as equal to 1 over root 2 pi sigma into minus infinity to something like the value of dosage with which I am interested into exponential of minus, again I write this because this is the starting point 2 sigma square into dx. This is the cumulative distribution. If I were to write this in terms of dosage, but we also said, I recall yesterday, we said normally the dosage is on the x axis, we put it in terms of logarithmic of dosage, such that we are able to put more dosage into the x axis. That means the small dosages get expanded out, the large dosages get contracted out. That is why we have a log scale, and therefore, the tendency is to plot it as a function of log d, or let us say ln d. And if I plot it as a ln d versus the value of x, well, if I were to write phi x, I can also write it as equal to phi x is the total response at the dosage d. Therefore, response at dosage d is equal to, I can write it as also, if the mean gets shifted, I can write it as 2p into minus infinity. The dosage gets started when I have d0. That means I have the dosage is ln d minus ln d0 into e to the power minus, I have a dummy variable u squared into du. This is one way of writing it. That is the cumulative distribution, which is the response, can be written in this form. And we just now said, well, the cumulative thing can also be written as 1 over 2 pi into minus infinity of the probit. This is equal to the value of the probit. This is the type of response what I get when my value is y minus phi, and that is equal to minus u square of du, or rather from this I can also write the value of ln d minus ln 0, which is along the x axis, which is precisely the same as the probit over here. Therefore, I get the value of ln d minus ln d0 is equal to y minus 5, probit minus 5, and therefore, I can write the value of y as equal to ln d plus 5 plus ln d0. For any, generally I can write this as equal to k1 plus k2 ln d. This becomes sort of like k1, I have some other factor coming in, maybe I try to non-dimensional, maybe log, ln and all that. Therefore, where I can write the probit as equal to k1 plus k2 ln d, where d is dosage, where k1 and k2 are known as probit parameters. And in general, for most of the explosions, most of the events which cause disaster, the k1 and k2 parameters are sort of available, and what one has to do is define the probit for a given dosage. Using the dosage, I can find out using the probit parameters the value of the probit, and using the probit and using the curve for probit, maybe the relation which we just now had for response versus the value of y for the probit, which is more or less linear, I can get at this value of y, well, this number of people get affected, and this is the use of the probit. Therefore, let us take a look at the probit parameters k1 and k2, and these are determined for different types of explosions. Let us say whenever I have a flash fire, the value of k1 is minus 14.9, the value of k2 is 2.56, where, as I said earlier, the value capital Y, which is probit, is equal to k1 plus k2 ln of the dosage. Similarly, for eardrum rupture from overpressure, the value of k1 is equal to minus 15.6, the value of k2 is 1.93. If I have glass breaking because of overpressure, we found that this overpressure was of the order of something like 0.75 kPa at which the glass bursts. The probit parameters k1 is equal to minus 18.1, the value of probit parameter k2 is equal to 2.79. Similarly, for dispersion of gases, the value of k1 is minus 37.98, the value of k2 is 3.7. Therefore, once the probit parameters are available, I can always calculate the particular response, and this is what we do to quantify the damages. Therefore, let me take one or two small examples to be able to illustrate the method by which we apply the probit. All what we do is, well, we said, well, we are interested in the total response. The total response is what we call as phi, that is a cumulative value, phi of the particular dosage. And we also said that the probit y is equal to k1, small k1 plus k2 ln of the dosage. And once you get the dosage is available to you, I can determine the probit. From probit, I can determine my response, how many number of people getting affected. Let's take an example. The number of people, total percentage of people or number of people who get affected when I have an overpressure of, let us say, 40 kPa. That means I have an explosion, and in the explosion blast waves are generated. You have at some particular distance a number of people who are standing around the explosion. Out of this, what is the percentage of people who lose their eardrums or their eardrum gets ruptured? Eardrum gets ruptured. How many? What is the percentage of people who get affected in a particular zone wherein the overpressure is 40 kPa? Immediately we tell ourselves, well, in this particular problem, if I could have the value of the probit for let us say rupture of eardrums, and that is available in literature, but I know that the dosage is equal to 40 kPa. Therefore, I say, well, what are the values of probit k1 and k2? This is available, and as is shown in this particular slide over here, the eardrum rupture from overpressure, the value of k1 is minus 15.6, the value of k2 is 1.93. Therefore, now I write the value, the value of the probit is equal to k1 plus k2 ln of d, which is equal to minus k1 was minus 15.6, k2 was 1.93 ln of d. Therefore, the value of y, in this particular case we say that the dosage is equal to 40 kPa, and therefore, when I say kPa, the dosage is expressed in terms of Newton per meter square. Therefore, the dosage is equal to 40 into 1000 Pascal, that is so much Newton per meter square, and therefore, the value of probit works out to be minus 15.6 plus 1.93 of ln of 40,000, and this gives me the value. If I solve for this, I get the value of y as equal to 4.85. I go back and look at the curve which tells me what is the value of response for a particular value of probit, and I had plotted this curve in the last slide. Let us take a look at this particular slide. When we have something like 4.85, we had something like maybe 50% of the people. Therefore, I look at this probit and I say, well, around 50% of the people get affected. Or if I want to use I am on the linear curve, I can also use the linear relation, and let's use that relation. That means I can write the response of the curve, response as r is equal to 38.2y minus 141, which is equal to y is 4.85, 38.2 into 4.85 gives me 185 minus 141, which is equal to 54%. That is 54% of the people who are in this range wherein the overpressure is 40 kPa will have their eardrums ruptured. This is the way to use a probit. Well, mind you, the unit of dosage is important. In this case, we said dosage is equal to 40 kPa, but when we looked at the dosages which we defined in the last class, we said that the dosage is expressed as Newton per meter square for overpressure. Let us take one more example such that the unit becomes a little more clear. Let us take a little more complicated example, in which case the dosage is a function of two parameters describing a particular explosion or a fireball. Let us consider the case of, maybe I have a fireball, the heat radiation from this fireball on to certain people around the fireball at some distance, let us say, is equal to the heat radiation, intensity of heat radiation is equal to 15 kilowatt per meter square. Let us say this fireball is there for a time equal to 1 minute. When we talk of in terms of the dosage for heat radiation from a fireball, dosage is defined as equal to IE, intensity of radiation, in watts per meter square, to the power 1.33 into effective time in seconds. This is the definition of dosage. Therefore, I convert this into watts per meter square, that is 15,000 watts, 15 kilowatts into 1.33 into time in seconds is 60 seconds. Therefore, the dosage comes out to be in this particular units of watts per meter square to the power 1.33 into seconds as equal to 2.15 into 10 to the power 7. The probit parameters K1 and K2 for the case of radiation from a fireball, which is again available, and this also was there in the slide, K1 is equal to minus 37.23. The value of probit parameter K2 is equal to 2.56. With the result, the value of probit Y is equal to K1 plus K2 ln of the dosage, in which case it becomes equal to minus 37.23 plus 2.56 ln of the dosage, which is 2.15 into 10 to the power 7, and this works out to be equal to 37.23 plus 43, this is minus, plus 43.22, which is around 6, and when y is 6, immediately I use the table. Let us say I go back to the particular response over this. I have the value of 6, and this 6 gives me a value around 85 or so, 85%. Or I use the formulae, and if I use the formulae, I can get the value again of response as something around 85%. That means 85% of the people who get who are affected, who probably get killed because of this radiation from the fire is this, and this particular value of probit was for the people who are killed by radiation from a particular fireball. And this is how we do the different problems. And maybe since we have been talking of glass breakage, let us do one last problem involving the effect of glass breakage from an explosion, that means window pane shattering. And in this case, the probit parameters K1 is defined as minus 77.1, the probit parameter K2 is defined as plus 6.91, and if I am considering a case wherein I have an overpressure delta P of, let us say, 0.001 75, or let us say I have 75 kPa, well, this pressure is extremely large. That means, well, all the 100% of the window panes will break. But if I were to now say I am looking at this overpressure, and these two probit parameters are for the case of maybe the lung getting ruptured, or let us say hemorrhage of the lung, well, these two parameters correspond to hemorrhage of the lung when I am talking of an explosion and the blast waves causing destruction to the lung. Then in this case the probit parameter y is equal to, I have K1 plus K2 ln D, and in this case I talk of delta P is equal to 75 kPa, in which case maybe all the glass breaks, but I want to find out the percentage of people whose lungs get affected. Therefore, 75 kPa is 75,000 Newton per meter square, and therefore my value of y is equal to minus 77.1 plus I get 6.91 into ln of 75,000, and which gives me a value of probit as equal to 0.47. You know, if I take a look at 0.47 in my particular figure, well, it is almost 0. That means none of the people's lungs are getting affected, even though all the glass windows get ruptured and all that, people are still safe. The response is 0 because my value of probit is so small that the response for this particular probit y, I have the response to be 0. That means nobody's lungs get ruptured, but since my overpressures are very large compared to something like we are talking of 0.75 kPa to rupture a window pane, I have something like 75,000, well, all the window panes get ruptured. This is how we do problems involving quantification of damages. Well, we have reached almost the end of our course, and in the next lecture we will take a look, having studied about quantification of damages, different types of damages and what a blast wave will do. Maybe we will try to take a look at what are the risks involved and do a small lecture on, have a small lecture on risk analysis, and this is what I do in the next lecture. Well, thank you.